Hi, my name is Alex Conrad, and I'm going to give you a brief overview of our paper on improved GPS-based single-frequency orbit determination for the Cygnus spacecraft using GipsyX. So just to give you some background, Cygnus is a constellation of 8 small satellites, each equipped with the GNSS reflectometry receivers. Its primary mission is to retrieve sea surface wind speeds from these reflections, but it also provides an opportunity to study the feasibility of GNSSR-based ocean altimetry. Previous work has identified the uncertainty in the Cygnus orbit as a primary error source for this, and so this paper is a focused effort to analyze and improve the Cygnus orbits. A high-level overview of our methods is that because Cygnus does not have any method to independently validate the orbits, we bring in the Cygnus mission to use that as an analog for understanding the errors associated with single-frequency POD solutions. GRACE has dual frequency orbit solutions that are much more accurate than we would expect to get with Cygnus. And so the goal here is to understand the errors associated with GRACE single frequency POD and the implications in that for the Cygnus orbits. We process 30-hour single frequency POD solutions, which are estimated using JPL's GipsyX software. To remove the ionosphere effect associated with single frequency measurements, we use something called the graphic method. This is just the code plus the phase divided by 2, and it results in an observable with half integer ambiguities and half the code noise. It also results in a loss of absolute timing, and so to deal with this, we include the code measurements within our POD to give the clock something to be based on, but we heavily deweight it in our orbit solution. Moving now to the results, we are first looking at the GRACE POD solutions. So from 30-hour orbit solutions, this results in 6 hours of overlap. From this overlap, we can compute the component differences during the overlap period. And that is what is being shown here for roughly 200 days of overlaps for the GRACE graphic solution. If we compare that back to the errors that we see in the graphic compared to the dual frequency truth orbit, we can see that the orbit overlaps are optimistic by about a factor of 2. Looking now at the Cygnus orbit overlap results, we can apply the fact that the GRACE graphic overlaps were optimistic by a factor of 2. This gets us to our overall goal of understanding what the errors associated with Cygnus are, and we would have an expected error of roughly 2.8 centimeters for the radial component, 2.4 centimeters for the cross track, and 6 centimeters for the in track. If you would like more information, you can read the paper or email me at alex.conrad@colorado.edu. And I would like to thank you for your attention.